Hi everyone. Unit 5 is ionic and covalent compounds. And once you've learned how to name the different types of compounds, we'll have to learn how to talk about the different ways of quantifying these compounds, the amount, whether that be in as a mass, or the amount of moles, or the number of molecules, atoms, or ions, etc. We'll also take a look at percent mass composition, another way that we can talk about the amount of these compounds. Okay, before we get to this video, is going to be pretty heavy on the calculations. You'll have some practice punching in numbers. But before we get to that, a little bit of bookkeeping. The first thing is mass, the mass of a compound. The mass of a compound typically can be given in grams or milligrams, kilograms, etc. That's a mass. But what about an amount? An amount of a compound, a number, could be given in moles. So moles, if you recall Avogadro's number, is 6.02 times 10 to the 23 something. Okay, and generically we could say particles. So a mole of atoms, okay, we could have atoms, is 6.02 times 10 to the 23 atoms. Half a mole of, let's say, ions, a half a mole of ions is 3.01 times 10 to the 23 ions. What else could we have? We could have atoms, we could have ions, we could have molecules. How about 2 moles? 2 moles of molecules would be 12.02 times 10 to the 23 molecules. How do you say that in correct or more proper scientific notation? Oh my goodness. So I said 12.04 times 10 to the 23 molecules per mole. Oh no, sorry, 12.04 times 10 to the 23 molecules. That's an amount. Proper scientific notation would be 1.204 times 10, and this is where I typically mess up. So that has to get bigger. Okay, so this has to be 10 to the 24. Okay, and if I move it 1 over 10 to the 23, 10 to the 22, okay, so 10 to the 24. Okay. So an amount can be in moles. Is that all I want to say for that? Yeah, there's actually one other thing I want to say. When we're going to be doing in these calculations a lot of dimensional analysis, canceling out units. When we're going to use Avogadro's number, I want us to think of it as a conversion, meaning that it's going to have units in the numerator and the denominator. Avogadro's number to me is it's still 6.02 times 10 to the 23, but I want to put units, and I'm going to say particles per mole. And that way, when we do our dimensional analysis, we could figure out how many atoms there are just by using 6.02 times 10 to the 23 atoms per mole, or how many molecules there are by using molecules per mole. Okay, you'll see that in just a bit. Is that all I want to say? Oh, no. One more bookkeeping item, molar mass. Okay, molar mass is the mass of a mole of atoms. So we could get the molar mass of chlorine, Okay, the molar mass of chlorine is 35.453 grams per mole. Okay, so there is a units, and it's going to be grams per mole. But not only could we get the molar mass of atoms, we could get the mass of a molecule or a compound. We'll say a compound of a mole of compound. And it's going to be grams per mole. The way we're going to use the periodic table is we are going to use those numbers under each symbol, each element, and we know that as the average atomic mass. So we are going to use the average atomic mass of the elements. I know this is, for a lot of you, very simple, but I do want to get these definitions formal because there are some students, I was one of these, where if the definition wasn't very clear in my head, then I had trouble using that term and I would get confused. I would get totally confused between what is the mass of compound versus its molar mass versus the amount if I didn't learn these definitions very strictly. So for the molar mass, we're going to use the numbers on the periodic table. Those numbers are the average atomic mass of each element. Okay. Let us get to the problem. Okay. If you want to pause, this is on a new sheet of paper. If you want to pause and copy this, or I don't know, take a screenshot or picture, this is a problem. I have an amount. No, I have a mass. I have a mass of magnesium nitrate powder. Initially, I had grams, but when I'm visualizing myself doing this, I'm not typically measuring out grams of powder, actually. I'm measuring out fairly small amounts, okay, milligrams. This is, well, I'll start us off. This is the same as you move the decimal point 3 times to the left, 0.0528 grams. Okay, this is going to be a little bit scary for me because I didn't do the calculations beforehand. I'm doing this fresh or doing these cold. So if I make a mistake, just let me know. Anyway, these are the problems, A through F. All right, let us actually read the problem. Pretend you just weighed 52.8 milligrams of magnesium nitrate powder. Answer the following. What is the molar mass of MgNO3 2? Okay, this is good. We don't need this amount. We just need the molar mass of MgNO3 2 for part A. I'm going to work back here, not waste any paper. The compound, the ionic compound, is MgNO3 2. And again, the question is simply, what is the molar mass? Question mark. Okay. When you're given a problem and you identify what they're looking for, quickly identify what units they want. Molar mass is grams per mole. So this is what our target is. Okay, that comes from our definition here, grams per mole. Simply, we're going to add up all the atoms and their average atomic masses, but we have to account for instance that there's not one nitrogen in this molecule. There's actually 2 nitrogen atoms in this molecule. All right, so let me show you how I would set it up. Magnesium. There's 1 magnesium, and magnesium average atomic mass is 24.305. Okay, I'm not going to put the units. Let me put the units at least for the first element. Okay, and we're going to get that number. But what about the nitrogen? See, the nitrogen is part of the polyatomic ion nitrate, NO3, but it's in parentheses, and there's a 2 after the parentheses. That means there are 2 nitrates. Well, if one nitrate has 1 nitrogen, 2 nitrates has 2. We're going to have this 2 times 14.007. Okay, and I'm not going to keep writing grams per mole. We know that it's grams per mole. Oxygen. Okay. Oxygen, we have 3 oxygens per nitrate polyatomic ion, but we have 2 nitrates, that is 6. 3 times 2. So that's 6 times, on my periodic table, it's 15.999 equals. Okay. It doesn't really say in the problem how many significant figures we should use. We're getting a molar mass. Why don't we go, I'll have to see what the number is, but probably, oh, we're really basing it off of the periodic table. I would just conservatively put 2 digits past a decimal. 2 digits past a decimal. All right, so this is 24.305. 2 times 14.007, 28.014, 6 times 15.999, 95.994. We're going to add them all up. Okay, don't round just yet. Just keep those numbers as is. Okay, I have 148, and then we could round. This is our final answer. I'll go to 2 digits past a decimal. This is not strict sig figs. Most of my average atomic masses have 5, right? 5 sig figs. Oh, it's 5. We'll keep it at that. Grams per mole, because again, we've identified that as our target units. And just because I'm a little bit worried I miscopied this, let me add them up one more time. Okay. 148.31 rounded. That is the molar mass of this molecule, this ionic compound. What does that mean? If I had a mole of this, it would weigh 148.31 grams. Well, obviously I don't have a mole. I have much less than a mole because I only have 0.0528 grams. Okay. We didn't use this number yet. We didn't use this in part A. But it looks like we're going to use it in part B. Part B says how many moles, there we go, of MgNO3 are in 52.8 milligrams. 52.8 milligrams is actually this. So now we're going to use dimensional analysis, because if I want to know how many moles, literally, we want the MOL. Now, I never mentioned it, but moles, the abbreviation, you could use MOL as well. Okay. And I did that over here, particles per mole. All right. Well, the cool thing about this is that if you know dimensional analysis, you know how to use those tricks. We need this targeting the unit mole, and we just calculate something that has grams per mole, and from our problem we have grams. Can we use those numbers to get grams per mole? I tell my students that you should start your dimensional analysis almost all the time with data and not conversion. This is data. Okay, it's a measurement. This, for part A, this is a conversion. It's per something, grams per mole. So I'm going to start out with the data, 0.0528 grams times. Okay. When in doubt, figure out your units first. Grams on the bottom, moles on the top. Well, we have grams and moles, or grams related to moles here, but we have to take the inverse because I want grams on the bottom. 148.31 and 1. Okay. It's good practice to go ahead and cross out or cancel your units. And I also like to circle the units that are left behind, that have not canceled out. That tells me that I hit my target units at least. 0.0528 divided by 148.31. Ooh. So we do have a bunch of zeros, leading zeros. Yeah, let's do scientific notation. And I don't want to get too crazy with the sig figs. We'll do 3, right, for this number here. 3 significant figures. 3.56, okay, times 10 to the 1, 2, 3, 4, times 10 to the negative 4. And what are the units? Moles. MOL or MOLES. Okay. I just want to make sure again, because I believe the way the questions are asked, we are building upon the previous part. Okay. 1, 2, 3, 4. Oh yeah, I'm good with that. Part C. How many molecules are in that many milligrams of MgNO3? Where do we see the word molecules? We see that, or can see it with Avogadro's number. Here I have particles, but we could have molecules per mole, atoms per mole, ions per mole, and it's still the same number. Just like you have a dozen marbles, that's 12. You could have a half a dozen pencils, that's half a dozen is 6. Okay. Okay, how many molecules? Let me start the work on this page actually. Okay, we are now on letter C. Right now I'm not seeing it. So let me just put down my target, molecules. I do have that, but in the previous problem I do have moles. Okay. And what is that? Moles of magnesium nitrate. Let me do that. 3.56 times 10 to the minus 4 moles. Okay, that's now my data. Times, I gotta get rid of moles and have molecules. I could do that. We have molecules on the top, and we have moles on the bottom to cancel out the moles. Okay. This is where to use Avogadro's number. 6.02 times 10 to the 23. That's the only conversion I know that relates molecules to moles. Okay, Avogadro's number. I still have that number saved in my calculator, the number of moles. The number's going to be much bigger than this, right? 6.02 times 10, so I use the E button, to the 23 equals. Okay, now it's in scientific notation. 2.14 times 10 to the 20. What do we want? Molecules. Molecules of what? Molecules of MgNO3. And actually, I'm going to put the compound now as part of the units. Okay. Part D. The reason why I put that because I read a little bit of ahead, because if I know the molecules, the number of molecules of this, I could figure out how many atoms of each element I have. And the first one is how many magnesium ions. Magnesium ions does your sample have? Well, my sample does have this many molecules of MgNO3 too. That's what I'm going to start out with. 2.14. And I am going to be, again, strict with the units. And I do want to put MgNO3 too. So molic for molecules. Why do I want to do that? NO3 2. I didn't put the question mark and pink just yet. For D, I want to know ions. Mg 2 plus, the number of those. Do they want moles? No, they don't want the moles of magnesium. They want the actual number of ions. Well, I have this number, and when you're converting the type of compound you have, like a compound to an atom or a compound to an ion, it's good practice to make sure you put the substance, because I'm changing the substance. I want Mg2 plus at the bottom. Okay. Oh no, I don't want Mg2 plus. I want this at the bottom. So how do I do that? How do I get rid of that unit and be left with this unit, 2 plus? Okay. We have to analyze our compound, our ionic compound. And for every one molecule of this, we have we have one ion of that. Did you hear what I said? So every one molecule, okay, we have one ion of Mg2 plus. Now, some of you who have done this or remember doing this in high school, you could even say, the ratio is still 1 to 1. So you could say 1 mole of this and 1 mole of Mg2 plus. The thing is, I like to use molecule because literally I am canceling out the word molecule. And I'm left with ions of Mg2 plus. Oh, it's just multiplied by 1. So I have 2.14 times 10 to the 20 ions Mg2 plus. Okay, was it really necessary for me to do dimensional analysis? In my mind, just for my peace of mind, it was necessary for me because I want to see those units cancel out and be left with the units that I want my answer in. Now we're up to E. How many oxygen atoms does your sample have? We're going to still use a molecule. Should I do that? Yeah. I'm still going to use molecules of MgNO3. Times. Again, when you are changing substances, I highly, highly recommend to my students you put down the substance and literally cancel that out. 1 molecule of MgNO3, 2. So what do I need? I need atoms of oxygen. Atoms of O. Well, how many atoms of oxygen do I have in 1 molecule of MgNO3? I have 6. I have 6 atoms of O. That number is still saved, I think. Yep, that number is still saved. Just times it by 6. And round 1.29 times 10 to the 21. So there are more. There's obviously more atoms of oxygen than ions of Mg in this ionic compound. 10 to the 21 atoms of oxygen. That's part E. We're running a bit long, but I did say that I want to talk a little bit about the percent mass composition. Percent mass composition. That is letter F in our case. What is the percent of oxygen by mass? That is super important. By mass. Okay, not by amount, not by number of atoms, right? But by actual grams of your sample. That's an interesting question. The thing is, we do have the molar mass of MgNO3. If I'm looking for a percent, right, that is part over whole. times 100%. Okay. For instance, if you shoot 85% free throws, that's 85 made out of 100. So the whole in my mind is this mass, the molar mass, and the part is going to be the molar mass of my oxygen, but of my 6 oxygens, because there are 6 oxygens that are, that are picking up the weight of this complex, that are part of the weight of this complex, or the mass of this complex. Okay, so 6 oxygens equals, I want the molar mass of 6 oxygens. 6 times 15.999. Okay, that is 95.994. And yes, I will use grams per mole. Okay. That is the molar mass of 6 oxygens. But the molar mass of the whole, which is MgNO3 we solved before for part A, that's 148.31. 148.31 grams per mole. You see how if I put the units as grams per mole, those cancel out. Grams per mole over grams per mole cancel out. And to get the unit as a percentage, you multiply this by 100%. It just worked out that every time I did a problem, this number was saved from the previous problem. 95.994 divided by 148.31 times 100. Okay, it has to be less than 100%. And in this case, it is 64.7%. Mass is oxygen in MgNO3 2. Okay. Again, what are we doing here? We're converting a lot. We've converted molar mass into mass. We converted moles into amounts of ions or amounts of molecules. All right. So that's all about converting, or I think people use the word interconverting between these units, right? And then the last one was percent mass composition. Okay, practice, practice, practice. This is important because, especially when you get into lab, you are literally weighing stuff, right? You are literally going to weigh stuff, and you got to know how many moles that is, or how many, less likely, but how many molecules that is. Okay, moles is actually the main workhorse unit in terms of understanding amounts. All right, good luck.